Good morning. Next we are going to see the fourth and last unit of Module 4, Work and Power, where we are going to apply what we have learned in the previous 3 units. As a review of concepts and expressions, we have this table in which I am not going to go deeper. It is simply available here. And we can see that it consists of the general definition of work with its curvilinear integral complicated to solve the general, and a table with the most common cases with their simplified formulas, which are the ones that were seen in the second unit of the module. Also on the right we see the definition of power and the relationship it has with force and velocity, and a summary following the third unit where we say the properties and definitions of conservative force and non-conservative force. All this is what we are going to apply next throughout this unit. In the first exercise we have J pushing a 30 kilogram box by a plane inclined 10 degrees with respect to the horizontal, so that it rises with a constant velocity of 0.2 meters per second. That is to say, the force that applies is the necessary one, strictly so that it stays in rectilinear and uniform movement. The coefficient of friction with the ground is 0.1, and what is asked is to obtain the work of each of the forces acting on the box to travel 5 meters. Obviously, this will require identifying these forces, knowing their values, and then with the formulas we have seen calculate their corresponding work. As an additional part, they also ask to find the power of the force exerted by Jota on the box. As you already know also from the previous module of point dynamics, the first task is to make a diagram where we represent the object under analysis, the box in this case, and the forces acting on that object. In this case, we have the weight, the traction by the earth, the forces that exist due to the contact with the ground, a normal reaction and a friction force, and the force exerted by Jota, which are there represented by those red arrows. As a result, we know that acceleration is a fact, that it is 0 vector meters per second squared, as corresponds to the fact that the velocity is constant. We are going to need a coordinate system that we are going to represent here, not for being obligatory but for being the most comfortable, since in this way 3 of the forces, the one exerted by Jota, the friction force and the normal force, are parallel to the axis, and the only one that has obliquity with respect to them is the weight, with which we would have complicated only to extract the vectors of one of these forces, the weight in particular. For this we have to know that it is the 10 degrees. One way to look at it is that if this is the angle formed by the horizontal ground with the plane rotating 90 degrees, the whole drawing we have precisely the same angle, 10 degrees, which is the one that is represented right now on the screen between n and the vertical. In this way we can pose the corresponding equations by Newton's second law. First, according to the x-axis we have that the components in that direction of the forces involved, Fjx component, the force exerted by J, Fr with sine minus the x component of the frictional force minus p sine of 10 degrees is the x component of the weight, and the normal reaction has no x component. So there is nothing to add here. All that equals mass times x component of the acceleration equals 0, because there is no acceleration. From there we can clear one of the unknowns, the force exerted by Jota. On the y-axis we do the same balance. In this case, Fr and Fj have no y component but have the normal. And the weight minus p cosine of 10 degrees. The sum of both components is 0 again, because there is no acceleration. From this we can solve the value of the normal ratio, which modulus it has, and it turns out to be 289.5 newtons. From this value we can determine the frictional force. Since the object is sliding, the frictional force is the maximum viable, mu, coefficient of friction times modulus of the normal ratio. The calculation with the above values gives us 28.95 newtons. With this value in the first of the equations, which allows us to obtain the force exerted by Jota, it turns out that this force is 80 newtons. So we already have the values of the forces to be able to calculate what we are now going to address, their corresponding work. We start with the work of the weight. The weight is a force that forms an angle, oblique with respect to the displacement that we are seeing in green. That green line would form or measure the corresponding meters, 5 in this example, and the angle formed by the weight is 100 degrees, 90 plus 10, to know where that number comes from. Applying the formula that corresponds to constant forces as vectors, which are oblique with respect to a straight trajectory, we know that this work is tangent force times d. In this case, the tangent force will be mg times the cosine of the 100 degrees, and that multiplied by 5 meters, which will be d. In summary, gives minus 255.3 joules. Note that it is negative because the cosine of 100 degrees is negative since it is an obtuse angle greater than 90. Also, it is to be expected because as we can see the force of, that is the weight, what it is doing is hindering the motion. So as it corresponds to that detail, the work of the weight is negative. As for the work of the normal is at all times perpendicular to the displacement. It forms 90 degrees anywhere, so we are with the particular case that we have seen in the drop-down screen on the left. In this case, the work we know has to be 0, and that value is the one we take into account. It corresponds to the detail that the normal reaction is neither helping nor hindering the displacement. With respect to the frictional force, the case is the one we are considering here. We have a rectilinear displacement and a constant force. We know it is worth 2895, and it also has opposite direction to the motion, so the corresponding formula is minus F times d. Therefore, that product gives us minus 144.7 joules. Thus, as expected, the work of friction is negative, as corresponds to the fact that it hinders motion. In fact, on many occasions I have seen incorrect calculations of the work of friction putting it as positive, which is impossible. Frictional work is never positive because friction never contributes to displacement. Always a work of friction is between 0 at most to minus infinity, from 0 to negative. The last force that remains to be considered is the force exerted by Jota. What work does it do? This is very similar to the case of the frictional force, with the difference that the force has the same direction as the motion, and therefore the corresponding force is force times distance. 80 times 5, 400 joules. It is curious, but I am not going to explain here yet why, that the sum of the 4 works you can see that it is exactly 0. It has to do precisely with the fact that the velocity remains constant, although to explain this in more detail, we will have to address the issue in the next module, that of energies. We still have to answer the last question, the power of the force exerted by Jota. Well, here what is more comfortable for us is to apply the formula that is equal to the force multiplied scalarly by the velocity. We could write the vectors as a function of the coordinate system chosen, but let's choose directly or do it with the general expression of a scalar product. Modulus of the first, 80, modulus of the second, 0.2 meters per second, cosine of the angle they form. We can verify that the force exerted by J and the velocity form an angle between them of 0 degrees, because they have equal direction and sense. The result is that this power is 16 watts. In that second exercise, we will see that J holds a pendulum whose length, understood by length, the distance from the fixed end to the center of the sphere, is 0.4 meters. The ball has a mass of 2 kilograms, and we are asked to obtain the work of each of the forces acting on the ball from the position shown in the figure until after rotating 50 degrees the pendulum is vertical. We will have therefore to identify these forces and from them to obtain the corresponding work. Here is the corresponding diagram. We have the pendulum in the initial position A, the pendulum in the vertical position B, and the angle of 50 degrees. We also have the measurements that we have discussed. The pendulum measures 0.4 meters at both the starting position and the target position. We need to get some measurements from this drawing, and let's see how to get them. To do this, I am going to use the triangle that I am highlighting in the figure. We can see that it is a right triangle with a hypotenuse of 0.4 meters, and where one of the angles is a known 50 degrees, which allows me to get the other 2 legs. Concretely, the horizontal one is going to be 0.4 sin of 50 degrees. And the vertical one is going to be 0.4 cosine of 50 degrees. So I have those measures. In addition, since this measure is 0.4 meters and I also know this one, by difference we can get this other value, which is the one that later, as we will see, we will need. Once the geometry is applied, it's time for the dynamics. Let's look at the forces. These are the forces that are acting on the ball: gravitational attraction, And then the only force that acts by direct action is the tension of the string. There's no other, we only have those two. One of them, the weight, is easy to determine. We know it's mg. While the tension is going to be much more complex because it doesn't have a constant value. It's going to change from position A to position B. So determining it is going to be quite complicated. As I say, it is a variable value. However, we will see that to get its work out, I will not need to know what the function of t is, how it changes. Let's start with the weight work. When we go from A to B, we have this case which, as we see, corresponds to that within the position A and B, the weight is a vector, a constant force. So the formula to apply is this: curved path with a constant force. The simplified expression is vector force multiplied scalarly by vector going from origin to destination. In this particular case, it means that we need a coordinate system. We are going to use, as it is the simplest in this case, the one shown in the figure. The weight is going to be mg downward, that is less mass by gravity by the unit vector j. Whereas the vector from A to B is going to be first a 0.306x component to the left, that is minus 0.306y, and then a minus 0.143j downward component. The scalar product by the usual methods of multiplying components turns out to give 2.80 joules. Note that it is positive as befits the fact that, in this example, the weight is contributing, is assisting the displacement. Let's look at a second, simpler way of calculating it. Recall that weight is a conservative force, so the work does not depend on the path. So let's break down the path. Let's make an alternative path, which is going to be the one that's now shown here in green. We're going to go down the straight line to point C, and then horizontally to point B, and the work is going to be the same. But it may be easier to calculate this way. Specifically, on the AC leg, we have a case like the one shown on the screen. Force in the same direction as the movement of constant modulus, so it is F times D, so it is M times G, times the displacement that we have here pointed out. In the section CB, it would turn out that the weight does no work because it acts perpendicularly. So the total is what we are looking at here. 2.80 of the first leg, 0 of the second. Total 2.80 joules. Obviously, even if it is not the real path, it does give me the same result, and therefore it can be a calculation tool and use a simpler path to calculate even if it is not the real one, as long as, I repeat, the force is conservative. As for the work of the tension, here we have, as I said, a problem. The tension is constantly changing. It is continuously changing its value. However, we can see that the tension always forms 90 degrees. It is always perpendicular to the trajectory at any of its points. Therefore, although T is very complicated to obtain, its work is very simple. It is simply 0. It neither contributes, nor helps, nor hinders the movement, the displacement. So I repeat, it is 0 joules. As a last exercise, this one is simpler, but we have to make derivatives. We will see this one. The work of the force generated by a motor from its start until the instant t follows the expression that we are seeing there in the international system. Therefore, putting you in seconds, we will obtain the work in joules. We are asked to obtain the expression of the power as a function of time. And what is the power if seconds after the start? We have there a graph showing how the work is as a function of time. Recall that the work is not a function of instant, but of interval. That is, when we represent in the graph, for example, what the work is worth for t equal to 3, we are actually referring to the work from t equal to 2t equal to 3 in that interval. We can see that it starts evolving more slowly, and in the end it ends up having a constant rate. Once the operation of that engine has stabilized, well, we simply have to apply the definition of power that it is the derivative of work. We only have to derive the expression, and we obtain the instantaneous expression of the power in the international system. Here we have the expression, that equation represented graphically. We can see that the initial power is 0, it is growing until finally it enters in regime. And let's say that we can see that asymptotically it tends to be 20 watts, which is what we have when the motor is already in permanent regime. As an example, the one that we are asked for t equal to 6 seconds, just replace in the equation and we get 19.95. To give you an idea, it would mean that at 6 seconds we are at 0.05 of 20, which is the target. That, if I'm not mistaken, would be 0.025% of what you have left to get to the permanent regime. Well, with these three examples, we finished this unit and therefore the work and power module.